purpose of this lab is to find the mass of a black hole by analyzing Newton's principle of momentum and net force. Using the given position data of a star that orbits a black hole, I created a computational model that found the net force and its two components, F net parallel and F net perpendicular, of the hole on the star. Then, I solved for the mass of the black hole by using the gravitational force equation, which was found to be approximately 2.67 times 10 to the 31 kilograms. Since we cannot see an agent contributing to the F net, we are going to assume the total force is due to a single gravitational force of the black hole. Here is a picture of the computational model at a certain position in the graph. The shorter black arrow represents the parallel component of the net force, which is tangent to the curve of orbit at the star's position and determines the change in the star's speed. The blue arrow represents the perpendicular component of net force, which determines the star's change in direction, and the yellow arrow represents the total net force on the system, which is what's used to calculate the mass of the black hole. To produce this model, I input the initial system properties that were given. For calculating the velocity of each time step, I subtracted the new positions from those of the previous steps and divided by delta t, which was 86,400 seconds, or 1 day. The equation of momentum is mass multiplied by the object's velocity, so with the velocities that I just calculated, I could use them in the equations for the initial and final momentum. To calculate the star's change in velocity and momentum, delta v and delta p respectively, I simply subtract their initials from their finals. Now, the whole reason why we are computing the initial and final momentums in this lab is to find the net force and its components to correctly observe the star's motion. Since acceleration is also equal to dv over dt, we can use Newton's second law, which has F net equal to ma, to be F net equal to m times dv over dt, or dp over dt, the change in momentum. Next, I calculated F net parallel, which I found by finding the change in speed of the star as it moves along the curve, or dp over dt parallel. To calculate F net parallel, I found the unit vector of momentum, p hat, the change in magnitude of momentum, dp over dt parallel, by multiplying p hat by the change in magnitude of momentum, and finally set that equal to the F net parallel. To get F net perpendicular, I found the change in direction, or dp dt perpendicular. Solving for this is easy now because we know the change of momentum as well as dp over dt parallel. Since the change of momentum is equal to the sum of the dp over dt parallel and dp over dt perpendicular, we can solve for the dp over dt perpendicular using this equation, and then finally set it to F net perpendicular. Using the net forces I found, I was able to create the accurate model of the star's motion as it orbits the black hole. Now I can finally calculate the mass of the black hole by using the equation to solve for our assumed single force, thus our net force acting on the star, the gravitational force, which is equal to the gravitation constant g, which is 6.67 times 10 to the negative 11th, multiplied by the mass of the star and the mass of the black hole, divided by the distance squared between them, or the radius squared of the star's orbit. I then solved for the mass of the black hole and found it to be roughly 2.67 times 10 to the 31st kilograms. Now, if the observed motion of the star was unchanged, but the black hole was replaced with a new one of a different mass, it would be impossible to solve for that new mass. The results from the analysis of the star's motion were all unique for that original mass. So if it were to change, then there would be a different gravitational force which would affect the motion of the star's orbit.